Okay, so today we are going to, okay, I'm recording ready. So today we are going to learn about thermodynamic process. Okay, there are actually 4 thermodynamic process. Isobaric, isochoric, adiabatic, and isothermal process. Okay, I just want to, I think I just want to write it over here. Okay, alright, I want to write it over here. So I start off with isothermal. I would like to start off with isothermal process. Okay, alright. Isothermal process. We have 4. Yeah, we have 4 processes: isothermal, adiabatic, isobaric, and isochoric. Okay, but I would like to start off with isothermal process, and then later on adiabatic. Below here we have isochoric. Isochoric has another name called isovolumetric. Isovolumetric process, and then finally we have isobaric process. Isobaric process. Well, isothermal. You know what is mean by isothermal? The word iso, it means what? Isotonic. Yeah, isotonic means same. Yeah, it means same or constant. Yeah, iso. Yeah, or it means only one. Understand? Iso means only one. Thermal means temperature lah, isn't it? Temperature. So isothermal means what? It means what? Class? You must respond. You must respond in the class. Yeah.
Same temperature.
Means isothermal means same temperature. Okay. And then so for this case, this one is temperature constant. Isothermal. And then isochoric or isovolumetric. What do you see here? This is same what? What do you think? What thing is constant?
Volume.
Volume. The word itself has volume, isn't it? Isovolumetric. So iso means constant volume. Or isochoric. Yeah, constant volume. And then here you can see isobaric. Isobaric. You know baric? Do you use before the barometer? Pernah dengar barometer?
Yes. Pernah.
Bar. In fact, the bar is actually a unit for what? Unit for pressure. Isn't it? Barometer is to measure the pressure, isn't it? So this one is what? What is constant? Class, what is constant?
Pressure.
Pressure is constant. That's very good. Pressure is constant. Okay, good. So now I want to continue our. Okay, make it a little bit wider. Okay, now isothermal. Isothermal temperature is constant. You learned before about temperature constant. Temperature is related to the internal energy. Still remember that? Okay, where is it? Okay, it's not over here. Never mind. Okay, let's look at our notes. Yeah. Still remember you learned about internal energy? Where do you learn about internal energy of gas? Internal energy of gas is the kinetic energy of gas, isn't it?
Yes, sir.
Internal energy of gas is the kinetic energy of gas, and it is depending on the temperature. The higher the temperature, the higher the internal energy of gas. Correct or not?
Yes, sir.
Okay. So, alright. So, let's continue. Okay, over here. So we can say you learn about internal energy is 1/2 F and KT. So here now he say temperature constant. Temperature constant, that means the internal energy also constant. So we can say if temperature constant, internal energy also constant. So the no change in internal energy, delta U is 0. Yeah, no change in internal energy, delta U 0. Okay. One thing is this. Okay, another thing is you learn about temperature constant. You learn about the the PV equal to nRT, right? PV nRT. Temperature constant is also called as the Boyle's law. Boyle's law. When temperature constant, that means you use this formula. P1 V1 equal to P2 V2. Because they are equal to nRT. This one is constant. Understand? This one is temperature is constant. So P1 V1 equal to P2 V2. Remember that?
Yes, sir.
So isothermal process is also Boyle's law. Yeah, because temperature constant. So the only thing changes is between pressure and volume. Pressure and volume. Okay. And all right. I just want to finish this. Boyle's law. Okay, if volume constant, isovolumetric or isochoric, volume constant, then is I call what law is it? What law is it? No. It's pressure law. It's pressure, or we call it Gay-Lussac law. Gay-Lussac law. Okay. So it's a P1 over T1 equal to P2 over T2. Pressure law, because volume is constant. Understand? And how about the isobaric? Pressure constant. Pressure constant, then is Charles' law. This is Charles' law. Charles law. Charles' law. Yeah? Charles' law, that means it's volume changes with temperature. Yeah, V1 over T1 equal to V2 over T2. Understand? Volume pressure constant, that is volume with temperature. If volume constant, then is pressure with temperature. Isovolumetric, volume constant, so pressure and temperature changes. Isobaric, pressure constant, so volume and temperature changes. Okay, enough with that. Now we go to just now I talked about the internal energy. We go back to isothermal process. Just now we talked about temperature constant, temperature related to internal energy of gas. So if temperature constant, that means internal energy also constant. So no change in internal energy. So delta U equal to 0. Yeah, because we can say delta T is 0. No change in temperature. Yeah, delta T is 0. Delta U is 0. Okay, and then look at the first law of thermodynamics. First law of thermodynamics, we have this formula. Where is our formula for first law of thermodynamics? First law of thermodynamics, delta U equal to Q minus W. Correct or not?
Yes, sir.
Delta U is change of internal energy, and then Q is heat flow, heat absorbed or heat release. W is work done. Yeah, work done on the gas or work done by the gas. Okay. So you relate to this formula. Okay, relate to this formula, and then we have what? Okay, first law of thermodynamics is delta U equal to Q minus W. Okay, so delta U is 0. Delta U is 0. So delta U is 0. So what do we have? So become work done equal to Q. Yeah. So go W, work go to the other side, become positive, and then Q. So this is the formula. This is the formula. Formula. Okay. For isothermal process. Okay, never mind. I think I just Okay. This is the and then another formula is this formula. This formula. Okay, good. And then what else we have? Okay, isochoric process. Isochoric process. Volume is constant. Volume is constant. Still remember about the volume? If volume is constant, that means no work done. Correct or not? Zero work done. Because if expansion, then only got work done, or compression. If volume doesn't change, means no work done. Okay, no expansion, no compression. Yeah, volume constant. So work done. For this one, work done is 0. Yeah, for isovolumetric, work done is 0. Okay, right over here. So work done is 0 because it say volume constant. No expansion, or compression. So no work done. Okay, work done 0. Okay, and then relate to our formula, delta U equal to Q minus W. Okay, delta U equal to Q minus W. So what do we have? So work done is 0. So our formula is delta U equal to Q. That's our formula. That's our formula. Okay. And then another formula is for this law is a pressure law. Okay. And then for isobaric pressure constant. Is it okay? Pressure constant. So does it change anything of the under this? Okay. Just now temperature constant. So delta U is 0. And then volume constant. So work done is 0. And then how about this? Pressure constant. Pressure has nothing to do lah. So delta U Q minus W, all also we have a value. So this one all has a value. So there's none 0 over here. And then there's the formula for Charles law. Okay, Charles law. Isobaric. Okay, how about adiabatic? Adiabatic, just now we already have delta U 0. Okay, let's see. Just now isothermal process, delta U 0. And then isovolumetric is work done 0. So what do you think for adiabatic? We already have delta U 0. Work done 0. How about adiabatic?
Q will become 0, sir.
Yes. This one Q0. This time, this one Q is 0. No heat flow. This one no heat flow. So delta U equal to Q minus W. So this time Q is 0. Q is 0. So this one is the formula is delta U equal to negative W. That's the formula. Yeah, that's the formula. Okay. So for this one, we already have temperature constant, volume constant, pressure constant. So the formula. This one Boyle's law, PV, P1 V1, P2 V2, P1 T1, P2 T2, V1 T1 T2, V1 over T1 V2 V2. This one actually all come from this formula. All come from PV equal to nRT or nKT, isn't it? So already have temperature constant, already have temperature constant, already have volume constant, already have pressure constant. So what about adiabatic? It seems that all changes lah. All changes. So we cannot. There's none constant for adiabatic. So for this one, all changes. Yeah, because you got change of internal energy. That means got change of temperature, isn't it? Got Got work done. Got work done. That means got change of volume, isn't it?
Yes.
That means pressure also must change lah. If that case, So if that case, this one, the formula will be just the ideal gas law. Yeah, ideal gas law. Is just use the one P1 V1 over T1 equal to P2 V2 over T2. That's the formula. Yeah, if you want to, still want to use the formula, this is the formula. All changes, none is constant. None is constant. This one at least got temperature constant, volume constant, pressure constant. Even the name itself, ISO temperature, ISO volume, ISO pressure. This one adiabatic, no ISO. So all changes. Pressure, volume, temperature, all changes. Actually, there's another formula, but not in syllabus. You're not learning this, but the STPM students are learning this. STPM students are learning this. They use adiabatic. They use this formula: P1 gamma over equal to P2 gamma. But this one is not in your syllabus, so no need to bother about this. Only ask the STPM student to bother about them. We don't have to bother. Okay. So ideal gas law, adiabatic use this formula. Okay, P1 V1 T1 equal to P2 V2 over T2. Okay. Okay, so that's the formula for adiabatic. Okay, we already got everything here. Okay, I want to wrap off. Okay, I have taught 9.4. This is all about 9.4. Now I want to go to 9.5, which is the graph. I want to talk about the graph. Okay. Now I want to talk about the graph. Okay, about the work done. Okay, about the work done. Work done is area under the graph. Okay, before that, I want to talk about a little bit about the PV graph first. PV graph. Let me have a little bit of description about this PV graph. Okay, so let me how to draw this. Okay, this color. Like that. Okay, now I want to talk about this PV graph. Yeah, before we move on. Okay, so we have pressure in unit Pascal. SI unit only. SI unit only. If atmospheric pressure, you need to change to Pascal. Yeah. Volume in meter cube. So, all right. So, we know that okay, got three direction. Okay, we know that going up. This one is maybe 1 Pascal, 2 Pascal, 3 Pascal, 4 Pascal. So we know that going up, direction going up is pressure increase. Correct not, class?
Yes, sir.
Okay, and then volume also going bigger and bigger. What is this? Sorry. Going to the right is also increasing. Going to the right also increasing. We call it expansion. Volume increase. Expansion. Okay, class.
Okay, sir.
Okay.
How to understand about temperature? Where is the temperature? Temperature is this line. This is temperature increase. So you don't understand, why? How come got another axis over here? Okay, actually it's like that. This pressure volume graph, we call it the PV graph. This is called the PV graph, pressure volume graph. Okay, it has many isotherm line. Isothermal line. Let me draw the isothermal line. Okay, let me draw the isothermal line. So isothermal line. Okay. All right. Okay. Like that. Another one lah. Okay? Okay? You satisfied? Okay. So, going away from the axis of pressure and volume, going away from the axis, the temperature increase. So that means the lowest line, it can be let's say 300 Kelvin, and then going up the line is 400 Kelvin, and then 500 Kelvin, 600, 700, and so on. This is imaginary number lah, imaginary number. In Kelvin SI unit also Kelvin Pascal, meter cube all in SI unit Okay, class. So when going away, so when going away from the axis of pressure or volume, the temperature increasing. So now I want one question. I want to ask you, what is the temperature between this point A, and point B? What is the temperature? What's the difference in temperature between point A and point B?
Same, sir.
Yes, they have the same temperature, which is... Okay, they have the same temperature. That's correct. Okay, because they are on the... We can say they are on the same...
Gradient.
Not gradient. Same isotherm line. We call it same isotherm line. Same isotherm line. That means along all this line, all the points, all the points along this isotherm line, along this 400 Kelvin line, they have the same temperature, 400 Kelvin. Understand or not? All the points along this isothermal line, we call it isotherm line. Isotherm line, same temperature line. Same temperature line. All the point around here is a curve, it's a curve. My curve is not beautiful. My curve is not beautiful, yeah? So your line is more beautiful than mine, yeah? Okay? So all the points over here, they have the same temperature. 400 Kelvin. So temperature at A and B is the same. Okay, but if you compare between A and, let's say A and where is it? A and C. C has a 600 Kelvin higher temperature than A or B. Understand? Because C is considered further away from both axes, pressure and volume. Further away. Pressure and B and A and B are considered almost same distance from pressure and volume lah. C is further away. So the line further away, they have the higher temperature. That's it lah. Okay. All I want to say. Okay. And then now I want to talk about. Now I want to talk about. I want to use this line also. Okay. Let me. Oh my gosh. Rub off all the points over here. Okay, I want to write something else. Okay, I want to write something else. Okay, so just now I put here A and just put this somewhere else, yeah. Okay, now let's say my graph is, now I want to make one. Let's say my graph is like this. My graph is from A go to B. That means my graph is this. My graph is this. Like that. Okay. Not beautiful. Not beautiful. Like that. Like that. This is my process from A to B. So I want to ask you, what happened to the temperature? Temperature increase or decrease?
Increase.
Temperature increase. Okay. This one, temperature increase. And then what happened to the pressure? Pressure?
Constant.
They have the constant pressure. I don't know what value. Yeah, Constant pressure. What happened to the volume?
Increase.
Volume increase. Yes. Volume increase. Yeah. Volume increase. So volume increase. So what process is this, class? What process is this? Isobaric. That's correct. Okay. So this is volume 1 and this is volume 2. What is the temperature? I can say temperature 1 will be 400 Kelvin. So this is the T1. Understand? And then what is the T2? T2 will be 600 Kelvin. Understand that? Then we can apply Charles' law over here. Understand? Charles' law. So V1, this is the V1. T1 is this is the T1. V2, this is the V2. And then T2 is the T2, 600 Kelvin, 400 Kelvin, and 600 Kelvin. Understand, class?
Yes.
Yeah. So this is considered isobaric expansion. This is what I mean by this is actually isobaric expansion. Isobaric expansion. Okay, this process AB is called isobaric expansion. If B go to A, that is isobaric compression. Understand or not? Isobaric compression. And then the pressure value has a certain pressure value lah. Okay. I will talk more about later on. Okay, how about graph like, for example, like, and I give another example. Let's say the graph now going this way. Like this. What happened to the temperature? What happened to the temperature going this way? From, let's say, from C to D.
Increase.
This one temperature increase. You see, you go to another isotherm line. Temperature increase. What happened to the pressure?
Increase.
Pressure also increase. This pressure C, and then this is a pressure D, right? Not? And then what happened to the pressure also increase? What happened to the volume?
Constant.
Volume constant. And then you also have the temperature C and temperature D, isn't it? This is what process? Isochoric, isovolumetric. Yeah, good. So that is the formula lah. P1 T1, P2 T2. Understand? Volume constant. Volume constant. So okay, I already got the two graph for this. And then what about isothermal? What do you think isothermal graph? Okay, let us draw one by one lah. So I already give you a rough idea about the graph going up is pressure increase, graph going to the right, volume increase, graph to the left, graph go to the left is volume decrease, go to the right expansion, go to the left compression. Okay, and then temperature going away, I mean the graph away from the both axes, temperature increase because we have isotherm line. Understand? Okay, you already got the idea. Now let's draw one by one for each process. Yeah, let's draw one by one. And then of course we need more space. We need more space. Okay, we need more space. All these are in your notes lah, but maybe certain points are not there. Yeah, so you can add up. Yeah, you can add up. Okay, let's draw the isothermal process. Okay. How to draw this? Isothermal process. Isothermal process. Let's draw the isothermal process. Okay, so now I want to draw the isothermal process. Pressure, Pascal, volume, meter cube, 0. Okay, isothermal process. That means it must have same temperature. So I need to draw the isotherm line. Let's draw the isotherm line. So the graph should be on the isotherm line, you understand? The graph should be on the
Yes,
isotherm line. Let's draw it. Let's draw it. All right. Okay, so 300 Kelvin, 400 Kelvin, and 500 Kelvin. 500 Kelvin. Okay, so isotherm line is like this. So isothermal process is like this. The graph is like this. The graph is like this. Come on, let me draw it beautifully. Isothermal process. So it's from, let's say, from A go to B. Go to B. Maintain the same temperature. Understand not? Same temperature.
yes, sir.
So this is the temperature lah. This is the temperature, yeah. And what's the pressure? So this is put this as, you know, this is pressure 1, and this is you know, this is pressure 2, and where is our volume? This is our volume 1, this is our volume 2. Understand? Initial pressure, initial volume, final pressure, final volume. And this is what we call isothermal expansion. Isothermal expansion, because volume increase. Do you see that? When volume increase, that pressure decrease. Do you see or not? Pressure compared to P1, pressure decrease, isn't it?
Yes,
See? Pressure decrease. Pressure decrease. Like, and then expansion, volume increase. You see that?
yes, sir.
When volume increase, pressure decrease. So this is a Boyle's law, but the temperature is constant. Okay. And then let's draw another graph for isochloric. Isochloric. Let me. Never mind. I just redraw lah. Yeah. I just redraw. Yes. Okay, let me redraw. Okay, so this is a pressure Pascal, and then volume meter cube, and then, you know, okay, so how to draw already? So I also draw the isotherm line. You have to show the difference in temperature. Yeah, show the difference in temperature. So okay, isochloric maintain the same volume. That means the graph should be, you know, the graph should be going. Let's say it's either going up or going down. Yeah, either going up, maintain the same volume, or it can be also going down. Understand? This one just now also can be either going down or going up. Understand? If going down is isothermal expansion, if going up is isothermal compression. Understand, class?
Yes, sir.
This one is this one is heated, this one is cool down, heated up, cooling down. Okay. Okay, so that's it. So from here I can get all the values, you know, I can get all the values. I have the volume given, and then I have the pressure 1 and then pressure 2, you know, and then I also have, you know, put this as temperature 1 over here, and then temperature 2 over here. Temperature 1, this one maybe 300 Kelvin. Yeah, this one temperature 2 maybe 500 Kelvin. Okay, so I have the temperature value, and then pressure value, and then constant volume. Okay, and that's it. And then how about the Charles law graph? So it should be okay. We are still have 15 more minutes. Yeah, we can finish that, including the work done also. Yeah. So okay, this is isobaric. Yeah, isobaric. What do you think? Same pressure lah. Yeah. Same pressure. Okay, same pressure. Also, I need to draw the isotherm line to show the changes in temperature. You understand? This isothermal line. I think I have repeated this isothermal line many times. I hope then by now you already understand and clear and remember, yeah, the things I repeat. Okay, so you know, the process also can be going to the left, not necessarily going to the right. But for this example, I just put, you know, it can be going to the right or going to the left. Understand? But I put it going to the right first. Okay, for this one is constant pressure. And then we have changes in volume V1 and V2. And then temperature, this is temperature 1, 300 Kelvin. And temperature 2 over here, 500 Kelvin. This temperature can be any value lah. I just put there the any just assumption value only, yeah. Okay, that's for our Charles law. Okay, pressure, and then finally, I don't talk about adiabatic yet. Okay, now what is the work done? How to find work done value? Work done. Work done is area under the graph. If you look at here, you see, this is area under the graph. Work done. Okay, if work done. Yeah, let's take isobaric. What is the work done? Work done is area under this graph. I just want to this is the area under the graph. Class, is this color beautiful, class?
Yes. Yes.
Okay, that's good. Okay. Okay, so how to find this area? Okay, let's find out. Yeah, let's find out what is the work done. So work done is area under pressure volume. Yeah, graph. I see. That's my kids. Okay. Okay, now let's continue. Okay, work done is, you know, area to work done is actually area under the graph. Area under the graph is actually integrate. You remember how to integrate?
Yes, sir.
Pressure versus volume. So area under PV graph. It's just like, you know, you still remember you want to find area of something. Area, let's say you have you know, y versus x graph. You want to find, you know, area of what you mathematic very hebat lah, yeah, very hebat. Want to find this area, yeah, the area of is integrate what y dx, isn't it, class? And then from x1 to x2, isn't it? You learn about integration already? Integration?
Yes, sir.
This is at maths in SPM, yeah, SPM. Hope you still remember. Okay. Okay, so it is the same lah, integrate, but of course the syllabus is not so difficult, need you to integrate, so we have simplified everything. Actually this is integrate from volume 1 to volume 2, integrate the pressure volume graph. So how are we going to do this? So from here you can see isobaric is a very simple process. It's actually a square, not a square, a rectangle, right? Not so how to find the area under this graph? Actually, you need to integrate, but because it's a rectangle shape, you just calculate the rectangle shape lah. So area under the graph, work done. That is to find the work done. So this is what? Pressure multiply change of volume. That's the formula. Pressure change multiply change of volume. This is the, you know, this is a pressure, and then this is a change of volume. Understand? So it's actually pressure multiply final volume minus initial volume, or we can say pressure V2 minus V1. Then you can find the work done. And then you can find the work done for isobaric process. Like for this one, the work done is positive or negative? This expansion, volume increase, isn't it?
Yes.
Because you go from, from A to B. V2 is bigger volume than V1. So this expansion, work done positive, isn't it? Because work done by gas. The piston, the gas do work done by gas. So if expansion, work done is positive. If let's say I have another graph, you see I need to draw another graph. Pity me, yeah. I have to draw another graph, and then if the graph is like this, how class? What is this work done? What is this is okay. So this is a compression. This is a compression. This is V1 and this is V2 lah. Yeah? This is V final and this V initial. Okay. This compression, work done negative, class. Work done negative because volume decrease. Understand not? This is work, compression is work done on gas. Work done on gas. For this one is expansion, work done by gas. Work done by gas. Work done by gas is positive work done. Okay, class? If the graph is going to the right, expansion, positive work done. If graph go to the left, compression, volume decrease, work done is negative. Okay. Now, how about isovolumetric? Isovolumetric. Is there any work done for isovolumetric volume constant? Is there any work done?
Yes.
Huh? No. No area, right or not? This area under PV graph. No area, so zero work done. Zero work done, Zero work done. You see that? Volume constant, no expansion, no compression, so work done zero, no area. So zero area. Understand? Okay. Okay, so we already got another equation for, for isobaric. We got equation already. Equation. Let's for equation, that's important. Yeah, just equation for isobaric to find the work done. That's the equation. And then for isovolumetric, work done is zero. Okay, work done is zero. And how about isothermal? Like for example, expansion. This one, what is the work done? Got area or not? Isothermal got area lah, isn't it? Got area under the graph. But this one is curved, not rectangle shape. So how to find area under a curve? You need to integrate law. You need to integrate law. Do you like integrate? Most of you don't like to integrate, I understand. So we have a formula for you. We already used integration, derive a formula for you. You just use the formula only. Yeah. For isothermal process, we have a formula. Yeah. After we integrate, we got a formula. Formula. So work done. Also integrate PdV from V1 to V2. Yeah, from V1 to V2. And what's the magic formula we got? The formula is nRT ln V2 over V1. This is the formula, nRT ln V2 over V1. Atau V final over V initial. Understand not? This V2 over V1 also can change into pressure. Look at here. This one, pressure P1 V1. Okay, I want to P1 V1 equal to P2 V2. So this one can further change into P1 over P2 equal to V2 over V1. Correct or not? Just interchange. V1 go below, P2 go below. Okay, so become P1 P2 equal to V2 over V1. Correct or not, class?
Correct, sir.
Correct. Okay, good. So this you also can change the formula into nRT ln P1 over P2. So it's either you use the V2 volume 2 divide by volume 1, or you use the pressure 1 divide by pressure 2. Understand? Pressure 1 divide by pressure 2. This one is V final over V initial. This one is P initial over P final. Don't worry, this formula will be given in the formula sheet. But if you can remember like me, better lah. Imagine a lecturer who don't remember any formula always refer to the formula sheet. So I take a lot of time to teach you if the lecturer itself cannot remember the formula. So it's a good thing if you can remember the formula, you do things faster. I see. So this is a formula to get the work done, area under the graph. Okay. And one more thing, class. Mostly, sometimes the question don't give you the temperature. If it don't give you temperature, how are you going to calculate the work done? So that's another way to calculate the work done without the temperature, without the number of mole. You know how?
Because
yes, correct. Because what? Because the this one actually, this P1 V1 P2 V2 actually come from the formula what? Come from the formula. Betul. P equal to nRT actually come from P1 V1 equal to nRT, ataupun P2 V2 equal to nRT because temperature constant kan? Because the temperature is constant kan? Temperature is constant. So P1 V1 equal to nRT temperature, P2 V2 equal to nRT also. So P1 V1 equal to P2 V2. That's how we got the Boyle's law. Correct or not, class?
Yes.
So this nRT boleh tukar kepada P1 V1 atau P2 V2. Another formula. Wow, today a lot you learn So P1 V1 ln V2 over V1, or you can write it as P2 V2 ln V2 over V1. Maksud saya yang bahagian ini. Bahagian ini I think this one you can change to P1 V1 ataupun P2 V2. Faham tak? Tapi jangan sesekali buat begini. P1 V2 pula. Ln V2 over V1. Ini janganlah, tolonglah. Saya doa lah. Bukan saya doa. Saya hadap lah. Kamu jangan buat begini. Boleh tak? Jangan campur adukkan. Point 1 means point 1 punya data. Point 2 means point 2 punya data. Okay? Jangan pula P1 V2 ataupun P2 V1. Boleh?
Boleh.
Inilah cara untuk cari work done. Okay, cara untuk cari work done. Work done punya formula untuk isothermal process. Okay, okay, bagi saya lagi 5 minit boleh untuk habiskan adiabatic. Kamu ada pergi ada kelas kah sekarang? Okay.
Boleh, boleh.
5 minit sajalah, 5 minit saja ya. Okay.
Boleh.
Habiskan. So ini formula dia. Okay, untuk work done. So kita sudah ada almost everything ya. Nota ini 9.4 and 9.5. Work done untuk isothermal, work done for isochoric and isobaric, work done, and all the other formula. First law of thermodynamics punya formula, and Boyle's law, Charles law, pressure law punya formula semua. Okay, now adiabatic. Adiabatic ini. Ini tolong jauh sikit. Oops. Wait a second. Let me just don't care about wait a second. Let's be patient a bit. Okay. Now, I want to talk about this adiabatic. Adiabatic. How is the graph look like? Okay. Why I put adiabatic same level with isothermal? Because I want to compare between isothermal process and adiabatic. Okay, because there's some similar things between these two. Okay, Okay, let's draw the graph. Yeah, let's draw the graph for this one, adiabatic. How does the graph look like? Okay, so pressure Pascal, volume meter cube, and then 0. Okay, so let's draw the isothermal line. Isothermal line. Okay, so put this as T1 300 Kelvin, and then this is T2 300 no 400 Kelvin, and then T3 is 500 Kelvin. Okay, so how is it looks like? Okay, firstly I want to draw the isothermal line first. Isothermal line maintain the same temperature, right or not? Going from, let's say, A to B. Going from A to B, isothermal is like this. Isothermal expansion. Okay? How is adiabatic? Adiabatic is steeper than isothermal. Dia pergi ke sini, C. Okay, remember this. Adiabatic graph is steeper. Apa maksud steeper? Lebih cerun. Ya? Lebih cerun. Steeper than isothermal graph. Lebih okay. Is steeper than isothermal graph. Dia lebih cerun. Faham tak? Lebih cerun. So dia lebih cerun. Yeah. So from here you can see already. So from here you can see. Okay, we have P1, we have P2, and then we have volume 1, volume 2, and then we have this one I shouldn't put. I just put. I think I just put as this one is T1. This is T2. Understand? Yeah, this is T1 and this is T2. So I have B1, V1, P for point A. Point A is P1, V1, T1. And then point 2 C, point 2 C is P2, V2, and T2. 300 Kelvin. So I can use the ideal gas law. P1, V1 over T1 equal to P2, V2 over T2. Whereas the isothermal process is maintain constant temperature. So this is isothermal expansion. This one is adiabatic expansion. Adiabatic expansion. Okay, adiabatic is steeper. Why is it steeper? Why? This one I need another 5 minutes to explain why. But first, I want to finish about the work done. Work done for adiabatic. How to find the work done for area under this graph?
Difference.
Integrate, is it? Integration, is it?
Yes.
Yeah. Do I have a special formula for you this time? Do you think I have a special formula for you this time? The answer is no. I don't have special formula for you this time. This one is
Not in syllabus.
not in syllabus. This time is work done for adiabatic. Work done of adiabatic is out of syllabus. So you don't have to worry about finding the work done for adiabatic. Understand? But it got work done. It got a work done, but it's just out of syllabus. You just have to find the work done for isothermal, find the work done for isobaric. That's all. Isochoric, isovolumetric is 0 work done because no expansion, no compression. Okay. So out of syllabus to find the work done. Okay, but the thing is just now, why adiabatic graph is steeper than isothermal graph? Why? Why the
Different temperature.
Yes, this one is different temperature. This one same temperature, maintain same temperature kan. This one may become different temperature. But why? This one need to explain another concept. Okay, another 5 minutes lah. Yeah, another 5 minutes. Make it 310 310. Okay, it's like this. It's like this. Okay, it's like this. Very easy only. Very simple only. So this one, I need to, you know, I need to explain one more thing. Okay, and then wait, let me see. Hold on a second. Okay, and then this one also. Why is it? Why is it? Why is it? Why is it? What is it? Why? Okay. A second. Okay. So, and then I need this information. I need this information. I need this information also. Okay. Never mind lah. I just write it again. Okay, class.
Yes.
This one isothermal, isn't it? Isothermal. That means temperature is constant. Okay. Adiabatic. Okay, temperature constant. That means U is constant. That means delta U 0, right? Okay, good. Adiabatic is no heat loss. Okay, like this. Actually, everything is happen in the piston. Everything is happen in the piston. Okay. Okay. So for this is a good conductor. This is a good conductor. Understand? This is a good what? Good conductor. For isothermal process. Isothermal is a good conductor. But for adiabatic, it is the bad conductor. As a bad conductor. It is you know, a bad conductor. Or we can say maybe it's insulated. You know, it's insulated. It's insulated. Somehow insulated. Insulated. Okay. Maybe it's good. Still good conductor, but it's insulated lah. Heavily insulated. Insulated. Understand?
Yes.
So like this. So like this. So like this. So like this. So like that. Okay. So how I'm going to draw it? Okay. Here got a piston. Yeah. Here got a piston. You know. Here also got a piston also. Okay. And then inside there is a gas lah. Inside of course there is a gas. Inside there is a gas. Inside there is a gas. You know that? Gas. Okay. So for isothermal process, it's a good. Okay, let's talk about adiabatic first. Adiabatic. No heat flow. Q equal to 0, right? Q equal to 0, that means the heat cannot flow in or cannot flow out. Heat cannot flow in or flow out. Understand? Because insulated. Insulated. So no heat can go out, no heat can go in. Understand or not?
Yes.
So okay, back to our first law. Our first law, delta U equal to Q minus W kan? So when Q equal to 0, so what's the formula become? Delta U equal to negative W.
W.
Correct or not, class? Okay. So now, let's say I want to expand. Let's say I want to expand. Expand. Okay. Expansion. Expansion. What happened to the volume?
Increase.
Volume increase. So volume increase, that means work done is
Positive.
positive. Good. Work done is positive. So let's put a positive value here. So become negative. Work done is positive kan? Work done is positive. So what happened? So negative time positive. What is the delta U? Delta U become negative. What does it mean? What is it mean by delta U negative? Delta U negative. That means internal energy decrease. Temperature decrease. Do you see that?
Yes, sir.
So when expansion, volume increase, the okay, my kids is here. Okay, I see a lot of challenges. Okay, so volume increase, work done is positive. So negative multiply positive, get negative. So delta U is negative. That means internal energy decrease, temperature decrease. So this internal energy, I mean the internal energy of this gas will decrease, temperature decrease. That means this gas will become cold. From hot become colder. So during expansion, during expansion, V1 go to V2, the temperature decrease. See that? Temperature decrease. So it cannot maintain at the same isotherm line. It cannot, let's say, start from A, it cannot go to B. It cannot go to B. It must go to a lower temperature. Do you understand that?
Yes, sir.
From 400 Kelvin must drop to 300 Kelvin. Must go to a lower temperature. If compression, excuse me.
Volume decrease.
If compression, then the other way around. The temperature should increase. If let's say from C, it will go to A. Temperature increase. If compression, it go to higher temperature. But if expansion, it go to lower temperature. Okay, this is actually conservation of energy. Do you actually understand why? Because when expansion, no heat can go in, no heat can go out, isn't it? No heat can go in, no heat can go out. So, but the thing is, this gas expand, right? This gas expand, so that means it's work done by gas. Expansion work done positive kan? It's work done by gas. Work done by gas. Gas has to do work. Gas has to do work. When you do work, you lost energy. Correct or not?
Yes.
So gas doesn't get any energy from outside because it's insulated. It's insulated. No heat from outside go into the gas. So, but the gas has to do work. The gas has to push the piston up. So where the gas get energy to do the work? The gas use what energy to do the work? He used his own internal energy to do the work, isn't it? Class.
Understand, sir.
He used his own internal energy to do the work. He use his own internal energy to push the piston up. When he use up his own internal energy to push the piston up, of course the internal energy will drop. The temperature will drop. That means the gas will become from hot become cold. Because no energy from outside can enter. See, no energy from outside. So it only has to depend on his own energy, own internal energy to do the expansion, to do the work. So when he use up his own internal energy to expand, to do positive work done, so of course his own internal energy will drop because he used up his own internal energy to do the work. When you use up internal energy to do the work, the internal energy will drop and temperature will drop. Understand? So so the gas will drop to a lower temperature. When expansion, it will drop to a lower temperature. Whereas the isothermal process can maintain the same temperature. But the thing is, the gas also expand. This one, the gas also expand. But why the internal energy doesn't drop? Why the temperature is still constant? For this one, let's look at the first law again. Delta U equal to Q minus W. This one, delta U, the internal energy maintain constant. Okay, so what happened to the work done? Work done is equal to Q. See that? This is because this one internal energy is constant. This one internal energy constant, temperature constant. You know why? Because this is a good conductor. Heat can easily go in. Heat can easily go up. Heat can easily go in and go out. So it's like this. This is like, it doesn't use its own internal energy to expand. He used energy from outside. It's like, you see, let's say heat absorb. So Q is positive, heat absorb. And then he used the heat absorb to do the work. Positive work done. Expand. Expand, we know that work done is positive. But at the same time, heat is absorbed. Heat is absorbed from outside. So he just used the absorb the heat to do the work. So his own internal energy is untouched. So no change in the internal energy. So that's why it can maintain the same temperature and same internal energy, constant internal energy. That's the isothermal process. Okay. So in short, what I can say is isothermal process. He used energy from outside to do the work, but adiabatic, he used his own energy reserve to do the work. That's why the isothermal process maintain the temperature, but adiabatic, the temperature will drop because he used his own internal energy to do the work. Okay, so that's all for explanation why the adiabatic graph is steeper than isothermal graph. So, can you understand?
Yes, sir.
Okay, so I think that's all yeah. If you don't understand, also never mind. Okay. Yeah. Explain this just to complete the lesson. Okay. So you also can listen back later on. But the important thing is more to how to draw the graph. Important thing is adiabatic must be steeper than isothermal process. And all those formulas that I explained, when expansion work done positive, compression work done negative, that one you must know. Yeah. And about this graph, yeah, I explained all that, isotherm line, all that. Yeah. So that's all for today, class. Yeah. Tomorrow we will finish off our tutorial question. Okay. That's all, and thank you. Bye.